Alright, now I hope you have your thinking caps on, because this one's tricky. Today we're going to talk about enthalpy. 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 Um, we're going to use it to explain this. Oh, hang on, we get my pen ready. Where are we? Get away, Carl Sagan. So what I want you to do. Escape. Alright, there we go. That's what I'm after. Alright, so we're going to use it to explain this equation here. Cool. And how we use that. We're going to explain how water's ability to absorb heat can be used to measure energy changes in a chemical reaction. We want to describe solutions that release heat as exothermic and ones that absorb heat as endothermic. Now, so we've got a lot on. These are kind of our goals right here, so we're going to skip the what's the point page and we jump straight in. So, an exothermic reaction, it releases, or the word we like, it should have an S in the end, is liberates. It liberates energy into its surroundings. One example is dissolution of sodium chloride. Okay, so when you dissolve sodium chloride, the temperature rises. Not a lot, but it does. Now, this here is a very famous exothermic reaction, and that was the Hindenburg disaster, where a bunch of hydrogen caught on fire, essentially. Now, endothermic reactions absorb energy from their surroundings. Alright, so the dissolution of sodium hydroxide. When you dissolve sodium hydroxide, you can feel it getting colder, and the reason it gets colder is it's taking energy away from its surroundings to make the reaction happen. Alright, so enthalpy and calorimetry. Alright, so a calorimeter, it's a piece of equipment we can use to measure heat changes in a change of state or a chemical reaction. So when those two things occur, we can use a calorimeter to measure the changes in temperature. Now, there's a thing called a bomb calorimeter, and page 265 of your text has an excellent description of that. But this one here is much more similar to what you'll see in the classroom. We have a couple of polystyrene cups, and the reason we use polystyrene is that they are excellent insulators, and you put two, so you've got a little air gap in between, which makes it an even better insulator. The inside cup itself is filled with water. All right, you have a thermometer in there and a stirrer, and whatever it's you're doing for your reaction, it's in this little sample tray right here, and that's a coffee cup calorimeter. Now, it's important that you just keep to a constant pressure. So there we go. To be honest, we'll do it by adding an aqueous solution, two aqueous solutions together, and then measuring the temperature change. All right, so you can also use it to measure the enthalpy of a system. It's coming. Be cool. System here implies enclosed system, so this means nothing can get in, nothing can get out, and it has to be a constant pressure. So enthalpy, H, is the letter we use to denote it, is the heat, hence the H, content of a system at constant pressure. Now, that H should be familiar, and that's because of the previous video we've done with an equation, which we're going to get into. All right, so, just to be sure, enthalpy is the heat content, the heat energy, the total heat energy of a system at constant pressure. Alright, so let's continue. Basically, a calorimeter can be used to measure the enthalpy change or temperature released or absorbed in a reaction. So when we release heat in a reaction, heat is gained by the calorimeter. Now, the opposite is true as well. When heat's absorbed by a reaction, heat is lost by the calorimeter. So when the heat is released by the reaction, we'll see the thermometer and the calorimeter rise. When heat is absorbed, the thermometer drops. Alright, so the total heat absorbed by the calorimeter is shown by the equation Q equals M times C, which is the specific heat capacity of whatever's in there, and so mass times the specific heat capacity times the temperature change. Cool, so Q is the quantity of energy absorbed, and C is the specific heat capacity, M is the mass, and delta T is the change in temperature. So quantity of energy absorbed. We're going to get rid of the Q in a second, but that's why it's there. So enthalpy is the sum of kinetic and potential energy of 1 mole of particles. So when we move from Q to H in a second, it's the mole of particles, which is important. All right, so it's not possible to measure the total empathy. That's enthalpy. It's not possible to measure the total enthalpy of a system, not really. So especially not in the high school lab. So we measure the change in enthalpy, and basically, the change in enthalpy is the products minus the reactants. So what you have at the start, you take away the reactants, whatever's left over, that's the change. All right, so let's have a look at some calculations. Now, as I said, this is a tricky one to follow along, so be prepared to pause, rewind, pause, rewind. All right, we use this formula here. Now, you'll notice that it's very similar to the formula for Q, because that one equals mc delta T. And you'll notice there's actually a fairly specific change. See, delta H is the H minus the reactants. All right, negative sign. That's important. Basically, if the temperature increases during a reaction, then delta T is positive, so that's high, and delta H is negative. So in an exothermic reaction, because temperature increases, delta H is negative. Okay, if the temperature decreases because energy is absorbed during the reaction, so it's taken away from the calorimeter, then delta T is negative and delta H is positive. So basically, a positive delta H is associated with endothermic processes. All right, now in your book on page 267, there are some sample problems. Read it, try it, cover the answers, see what you come up with. Then go through the sample answer and bring your sample answer that you've written to class, and we'll do it together. All right. I hope that wasn't too hard, and we'll see how we go.